Okay, we're going to pick up our discussion now in the second video, and now we have this question about Hoare triples. Are they valid or invalid? So certainly we can write down all kinds of nonsense in the form of a Hoare triple, but we want to know, is this thing actually true, right? Is it the case that if we do run this program with the precondition holding, that when the program terminates, the postcondition will be true? So in this case, we see an example that seems like this Hoare triple certainly is valid. If x is greater than 0, presumably an integer, we multiply it by 2, it's going to be even. Right? So this is something we could attempt to prove, but this certainly looks like a valid Hoare triple. This one here certainly looks incorrect. Right? If x is equal to 5 to begin with, we add 4 to x. It's not the case that when we're done, x is equal to 10. So this is an invalid Hoare triple, or an untrue Hoare triple. This one is a sort of a degenerate case, a strange case, because the loop never terminates. And so even though we do not suspect that x is odd at the end, well, since there is no end, we can't really say very much about this. And so Hoare triples are such that if the program does not terminate, we then consider that to be a valid Hoare triple, but it's not something we're going to concern ourselves too much with. The programs we're going to look at do terminate, and those are the ones we'll consider. But this is something you do want to keep in mind anyway. All right, so if we've seen invalid and valid Hoare triples, what we really need next is some sort of systematic way to know which ones are valid. And so what we're going to do is look at the semantic rules in the axiomatic semantics, and we want to see them as ways to generate valid Hoare triples. And so one issue we have is knowing what is true and when, right? Few things are true consistently through an imperative program. Imperative programs change the state of the program, and thus something that is true at one point, perhaps point A here, is not going to be true at point B. And so that's something we always keep in mind, and thus we consider properties to hold between statements. They are not properties of a statement. They are properties that hold before a statement or after a statement. All right, so here we go. We see the definitions again of preconditions and postconditions. And we also want to consider conditions that are true between the statements. So not just at the beginning of the program, at the end of the program, but we want to look at different points during the execution of that program. All right, we're going to look only at structured programs. So there's no go-to statements, there's no breaks here. And this reasoning process, because it follows the syntactic structure of the program, we can't do this nicely with unstructured programs. So we're only considering structured programs, and we know that's okay. We've seen earlier that go-tos are not technically necessary in our language. And so a key point here is that our proofs of partial correctness follow the syntactic structure of the program. Right, so that's what we're really after here. All right, so Hoare semantics consists of two pieces, two types of pieces, axioms and rules. Axioms, we consider these to be things that are always true, right? And rules are ways of generating new true statements. And we generate them from existing true statements. Where an axiom, either we consider this as a true statement, or we can also consider this to be something of a way to generate new true statements. But we don't require existing true statements to do that. All right, we'll next begin our tour of the axioms and rules in axiomatic semantics, and that is what we do in the next video.